Okay, the next topic for data representation, this is the first chapter of IGCSE O levels book. So the next topic we are going to study, that is binary addition. Now, in order to do the binary addition, we have to first understand these rules. These are the rules that when we add two zeros, we get the sum as 0 and no carry bit. When we add 0 plus 1, we get the sum as 1, of course, no carry bit. And when we add 1 plus 0, it's also the same, sum is 1 but no carry bit. But when we add the two numbers 1 and 1, 1 and 1, when we add them, we get the sum as 0, 1 goes to the carry. Okay, and if we do 1 plus 1, then what we have 1 as a sum and 1 as a carry. So this is how first one everyone must learn and understand this table, and then we can move forward for the binary addition. If you don't understand it at the moment, you must learn it, then you will know. Okay, now let's see. These are the basically rules in which we do some which we follow for the binary addition. Let's see what they are. Binary addition follows same method as denary. It is very similar to denary. Start from rightmost column, carry when sum exceeds 1, and continue adding including carry. Okay, let's see what it means. If we have to add two numbers 126 and 62, the binary of 126 is that if you want to learn that, you can read the previous lectures, so you will understand the binary conversion as well. So here what we have seen, we have seen this is the binary form of 126 and this is the binary form of 62. You can see 126 is a basically 7-bit number, so we have put the 0 to the leftmost to make it 8-bit. Similarly, this is basically 6-bit number 62, so we have put two zeros behind it. So let's see. Now we are going to add them. In order to add them, when we do 0 plus 0, the answer will be 0 here. And when we do 1 plus 1, answer will be 0, but 1 will goes to the carry. Now let's see. These are the carry bits for it. You can see 1 plus. Now let me go forward. So okay, 0 plus 0 gives us 0, 1 plus 1 gives us 0, and 1 goes to the carry. As we saw the table previously. You can see this table. 1 plus 1 gives us 0 sum, and the carry goes upper. So and let's move on. Now let's see again. 0 plus 0, what it will give us? It will give us 0. 1 plus 1 gives us 0. 1 goes to the carry. Now there are three ones, the carry one and the other one. So when we add all of them, one will be here and also one will be in the carry. So this one will also be added here. So then we get also one and another one to the carry. Then we also add these ones and we get this one and another one to the carry. Then there are again three ones, then another one to the carry. 1 plus 1 plus 0. Now 1 plus 1 plus 0, that will give us the answer as 0, and 1 will go to the carry. 1 plus 0, that will give us 1. So now you can see this is our final answer, 10111100. If you want, now let's see how to check it in denary values. In denary, 126 plus 62 gives us 188. If you convert 188 to binary, you will get this answer. So this way, if you get this answer, this means that our solution is correct, and this solution is absolutely correct. You will get this answer. If you let me verbally tell you, let's say you put the place values here. This value is 1, this is 2, double it 4, double it 8, double it 16, double it 32, double it 64, double it 128. Now when you add 128 with these values of 1, you will get 188 answer. Let's say how. This is 128 and this is 32. What 128 plus 32? 160. 160 plus 16, 176. 176 plus this is 8. 176 plus 8, 184, plus 4, 188. So this is solution is correct. Okay, there is another thing that we call overflow. It occurs when results exceeds 8 bits. At this moment, our result is within 8 bits. So if it exceeds 8 bits, then extra 9 bit is generated. That will be considered as overflow because that bit is too large. key point, maximum 8-bit value is 255. If any value is greater than 255, for example 256, that will come in 9 bits, so that will be causing an overflow error if our system is of 8 bits. Carry out the following binary additions. Now let's say if we carry out these binary additions, 1 plus 0 1, 0 plus 1 gives us 1 and no carry, 1 plus 1 gives us 0 and 1 will be to the carry, let's say. uh, okay, this one will add to this one, then again 0 and 1 to the carry, 1 plus 1 plus 0 again 10 and it gives us 0 and 1 to the carry, then 1 plus 0 plus 1 again 0 and 1 to the carry, 1 plus 0 plus 1 again 0 and 1 to the carry, 1 plus 0 plus 0, that gives us 1. So this is our answer. If you want to check it what this is, you can convert all of these numbers into denary and you can verify the sum. It is correct. Now there is another two numbers, 98 and 15. This is the basically binary value of 98. This is binary value of 15. If we have to add them, 0 plus 1 gives us 1, 1 plus 1 gives us 0 as sum, 1 as carry, and then 1 plus 0 plus 1 gives us 0 as sum and 1 as the carry. 1 plus 0 gives us 1 as sum and no 0 carry, so 1 plus 0 it will give us 1, 1 plus 0 will give us 1, so the final answer will be 0 triple 1 double triple 0 1. So that will be our final answer. That gives us the value, that this value will be equal to 113. 1 double it 2 double it 4 it and double it 8 double it 16 double it 32 double it 64. 64 plus 32 96, 96 plus 16 112 and then you add 1 to it and that is 113. So this solution is also correct. Now convert to 8-bit binary and add. So we have already studied the conversion from denary to binary, so you can see that these are the basically converted values and you can add them together in this with the same rules that we mentioned earlier. So this is why now, but here what you see, what's the unique thing about is that we have one overflow bit. It is in bold and this one is overflow, as both of these values are in 8 bits, but our result is coming in 9 bits, so this is an overflow value. So in 8 bit the result will be this, the overflow value will not be counted because that is coming into the ninth row, so it will give us the wrong result. What result that will be? 1,000 is equal to uh, what in binary? It is equal to 8 in binary, so that will give us the result as 8, which is absolutely wrong. 175 plus 89 can never be equal to 8. So this is how this error will consume us. Next, let's say if we have a 16-bit binary number. In order to add 16-bit binary number, if these were 16-bit numbers, so there wouldn't have been any overflow. The exact same method will be for 1 plus 1 equal to 0 and 1 will be go to the carry, and then 1 plus 0 plus 0 1, 0 plus 0 0, 0 plus 1 is 1, and then there's a stream of carries. 1 plus 1 is 0 and 1 is carry, so 1 and 1 is carry again. 1 plus 1 is 0 and 1 carry, 1 plus 1 plus 0 0 and 1 is carry again. 3 ones 1 and 1 is carry, 3 ones 1 and 1 is carry, 3 ones, and this goes on until this carry and 0 and 1 again. 3 ones 1 is carry, 1 plus 0 plus 0, that is 1. Result is also in within 16 bits, so this is also, there is no overflow. Now this is the activity that you all should be doing by yourself. You have to carry out these binary additions. You will do it the similar way, the way we performed our binary addition. And these are the this is also in these values. You'll have to convert these values into binary. And how you will convert them? You will convert them separately by using the methods that we studied in the previous slides, in the previous two videos. You will have to learn that first, and then you'll be able to carry out these additions. And you know how we do the binary additions. Now convert the following pairs of binary numbers to 8-bit binary and then add the. Okay, you will have to convert these into 8-bit binary, and we have already solved this question part A in there, so you will do it that way. another, and we have also done the 16-bit binary number addition, so now you are much familiar with that as well. So this is the homework that you all should do. That is already present in the lecture, but what you have to do, you have to first, if you don't understand this binary conversion, binary to binary, then you'll have to do it from the previous lecture. Okay, you all should follow the lectures in the correct sequence. Only this way you won't be need to any revision of the previous lectures. So you'll just have to first understand the first lecture fully and then move on to the next lecture. Okay, next topic is our logical binary shifts. Logical shift means moving binary digits left or right. Okay, you'll have to move the binary digits to the left or right. How? Let's say empty positions are filled with 0. Any position that be empty, that gets filled with 0. Used in computer processing. Let's say how? Move bit to the left. Each shift equal to multiply by 2. Each shift is means we are multiplying that digit by 2 and we are replacing the current position with 0. Let's say, and then there is a right shift. Right shift means we are dividing the values by 2. How? Let's say this is the part that key terms most significant bit and least significant bit. You already know rightmost bits are the least significant, leftmost are the most significant. Now let's say this is a number binary number 21. This is its binary. If we left shift it towards left, what will be 2? If we left shift it towards left, then it will be doubled. The number it will the new binary will show the number 42. Let's say, let's see how. Okay, one left shift. When we have shifted it towards the left, one left, let's see how. This one will be shifted here. This 0 will shift to the ones place. This one will shift to the zeros place. This 0 will shift to the ones place. And this one will shift to this zeros place. So if this one is shifted to this place, what will we have at the end? We will automatically put a 0. When we automatically put a 0, so this is how we have put the 0. We have shifted this one here to the left, so we are left with two zeros behind, so two zeros and 1. We have shifted next 0 to this, so we are left with 001 behind, and this is how the value comes. Okay, now let's left shift it to second time. If we left shift this value again, so it will become double of 42, that will become 84, and this value will be what? Let's say now we have shifted this one to the left, this one is shifted to the left, so this is not 00 behind, it has only 10 left. And again this 0 is shifted to the left, so this 0 and this one is shifted to the left, so 0101. This 0 is shifted to the left, 010 and this one is shifted to the left, this one is so, and this 0 is shifted to the left. So and now in the end one space is empty, so that will also be filled with the 0, so that will become the number 84. If we shift it again, that answer will be equal to 168. You know, if we shifted this one to here, so at the end most significant will become bit will become 1, as we have replaced it with the right, not just replace not yes, we have moved right bit to the left position, and now the leftmost zeros are gone. So again this 0 will shift here to the second place, this one will shift to the third place, this 0 will shift to the fourth place, this one will shift to the fifth place. Now in the end there are two zeros are already there and one zero's position is left, so we will put that 0 ourselves, and this will become a, this is what we call a left shift. So this is how important concept. Each shift multiplies by 2. Each left shift multiplies by 2. Excessive left shifts cause loss of most significant bit. Now, if we do another shift to it, so we will lose the most significant bit and we will get the answer as wrong. So result becomes incorrect. Now, if we do the right shift, we right shift our values. If we right shift our value, that is 200 is equal to this in binary. If we right shift it, the answer will be equal to 100, because right shift means we are dividing it by 2. And if we again right shift it, then the answer of that will be 50. Let's see how. Now we have right shifted these values. You can see uh, we have right shifted this value 1 to the right. We have shifted this value 0 to the right, it is gone. We have shifted this 0, it comes to the end. We have shifted this 0, it comes to the second last position. We have shifted this 1, it comes to this position. We have shifted this 0, it comes to the position where we had previous 1. And now again, similarly, we have shifted this 0, we have shifted next 0, and now we have shifted 1 to the right, and this one is also shifted to the right. On the leftmost significant bit, we are now left with no bit. When are left with no bit, then we put 0 there. So this will become 011, and this value is exactly equal to 100 in denary. Again, if we shift it to the right, that will become 50. So we have again shifted it to the right, shifted this one. So on the right side, there's only 1 0 left. So we have again shifted it to the right. This becomes this. We have shifted to this to the right. This becomes this. So this similar way, this is how we have shifted all these values. Now we have, after this is the third shift, so the value becomes 25. Each shift is dividing it by 2. Excessive right shifts cause loss of least significant bits. Now if we right shift it again, we will lose the 1 and we will get an incorrect error, incorrect result. So that result will be equal to 12. So that 12 is half of 25 is not 12, it's in the some decimal value. So that will become 12. So that will be an incorrect result. Now we have another number 24 in binary. We have what we it is asking us to shift 2 left. When we shift it 2 left times, 1 1 2 left, this one is 1 1 2 left, and there additional zeros will be added, and is how it becomes 96. 24, double it with one shift, that is becomes 48. Double it with one another shift, that becomes 96. Now we have now what this is asking, it is asking us to shift it three times right. If we do 3 shifts to the right, or shifting zeros doesn't matter, because that will answer will remain the same. um, One shift, second shift, and third shift. So third shift will put the 1 here. Okay, let me see. If we divide it by, it will be divided by 2, that will become in 48. 48 will become 24. 24 will become 3. Oh, okay, let me see. Let's say let's right shift this value. Let me pick up the pen. We have the values 0 double 1 for, okay, I don't have the stylus at the moment, so that is why please bear with me. 0 double 1, and we have 5 zeros here. Now let's shift it three shifts, 1 2 and 3. So here we have another 1. Now if we shift this one 3 times, 1 2 and 3, so this one will come here. So now what we left with, we are left with only zeros behind it. How many zeros we will have? Numerous zeros, 1 2 3 and 4 zeros. Okay, we have to shift this 0 as well, 1 2 and 3. So here we'll have a 0, and now we will put we have shifted 3 times, so we will be putting 3 zeros towards the left, and triple zero, 0 double 1, that becomes 6, and double 0. So that will be our then value. Okay, so this is I think this is a little wrong answer. Let's say answer won't be the 3. This will be our answer, that will be 12. As we have shifted 3 times, so our answer will be 12. Let's correct it. Okay, so this answer should be 12. We have shifted 96 3 times, so we will get the answer as 12. Let me do that again. As we will get double 1 double 0, not 3. So our binary will be equal to 1100. As we have shifted 2 places left and 3 places right, so this will be our answer. Now you can understand that again this is answer is 12, not 3. Now you all must try to understand that. Now this is the value 19 triple zero one double zero double one, and this is 17 triple zero one triple zero one. So this value gives us the value 19 and 17. That's the difference. So these are their binaries. Let's say what it is asking us to add these values. We have already studied addition. 1 plus 1 gives us the value 0 and 1 as carry, and 1 plus 1 plus 0 again 0 and 1 is carry. 1 plus 0 gives us 1, 0 plus 0 plus 0 gives us 0, 0 plus 1 gives us 0 and 1 as carry. 1 plus 0 1. Then so the value is this. Now the now if we shift that value to 2 places left, okay, if we shift 2 places left, one will become the most significant bit here, and this one is has become the most significant. This one will come over here, and so our answer will be 1001 and next zeros afterwards. So that result will be 144. How? The result, the answer of this value is, if you convert that into decimal, that will be 36, and 36, double of 36 is 72, and as we have shifted 2 times, so double of 72 becomes 144. Now we are shifting 3 places to the right. Let's see what our answer becomes. If we shift 3 places to the right, our answer should become 18. Let's see how. And this answer will be 4. That will be wrong answer if we give 4. But why is it saying if we shift it 3 times, then we will lose the most significant bit. We lose the least significant bit, and that this way our answer will give us the wrong result. But I think this one is a little 1, 2, and 3. Yes, we have shifted this one 3 times, 1, 2, and 3. So that will give us the wrong result. Uh, and in if you can see, uh, we will lose this bit, so we will get the result as this. So that will we will get the wrong result, and that here we will have error due to loss of bits. So that is, we must take care of this thing when we are doing shifting, left right shift, because it is important. It is used in programming coding, so we'll have to be careful with the right shift and left shift operators. This is the formative assessment that every student should do. You will be using these same methods that we followed here. So, and I've also given you the solution in the next slides. This is the basically binary value of this value 64 plus 32, and we have already studied right shift. So if we shifted these to the right 3 places, you can just bring all of these as 3 places to the right. One is shifting 3 places to the right, it will become 1 will come here, 0 will come here, and 1 will become here, and so this is how it will work. We have shifted it 3 times. Let's say whether we got the correct result. Divide. Uh, okay, 1101. We have shifted it to the right. Its value is 104, and 104, dividing 104 by 2, we get 52, and with one shift, and when we divide that by 2, in the second shift we will get the result 26. If we divide that by 2, we will get the result 13. So with 3 shifts you get the result 13, and basically 13 is basically what gives us the division by 2. 13 multiplied by 8 gives us 104. So when we divide it 3 times by 2, that is means we are dividing it by 8. Right shift divided by 2 cubes, so that gives us the value. And there's another question, denary value of this. We have to add use this method. If you want to study denary in detail, you have to go to the lecture 1 and lecture 2. Let's say we have to shift 4 places left. Now there we will lose the loads of bits. No, we are not losing any bits. We are just shifting. We get the without losing bits, we'll get the number 240. This number is 15. Double one equals to 15. If we shift it 4 times, we means we multiply 15 by 16. That gives us the 240 result. And this is another number, convert 29 and 51. We have already studied how to convert these numbers, and after the conversion you can add them, as we have already studied them. Shift result 3 places right. Now when we shift this result 3 places right, this will become all 101 will come up to 1 place, 2 places, and 3 places. Oh, let me see if we one, two, three. Yes, 101 will become here. It will be, and we'll add zeros towards the back of it. So this will give us the result 10. Okay, this result is 80. If we divide it by 8, it gives us 10. Now there's another number 75. If we convert it into binary, it becomes this. You can study that in the previous lectures. Add 75 and 10, or you can get this is how you'll add the binary addition. 0 plus 1, 1. 1 plus 1 is 0, and 1 is the carry. 1 plus 0 is 1. 1 plus 1 plus 1 is again 1, and 1 is to the carry. 1. Oh, I think let me correct it again. 0 plus 1 gives us 1. This 1 plus 1 plus 1 oh, there is a mistake in it. Let me correct this thing. 0 plus 1 is 1, 1 plus 1 is 0, and 1 plus 0 plus 0 is 1. Then uh, then we have, after that we have 1 plus 1 as 0, and okay, it is correct. Then this 1 plus 0 plus 0 gives us 1, and again next rest is 0 plus 0 is 0, and 0 plus 1 gives us 1. Oh, it is correct. The answer is correct. We can verify it. Let me re-verify it again. Actually, this one is a little right side. Let me correct it by placing it here. I think this is a little better, but it is still showing us the wrong result. Let's keep it there. 1 plus 0 plus 0 gives us 1. Yes, the 1 plus 1 gives us 0, and then 1 goes for carry. That is it. Now, if we were 1, 2, 4, 8, 16, 32, 64. 64 plus 16, 80, 80 plus 4, 84 plus 1, 85. So that is the result is correct. Now shift final result 1 place left. Now if we shift at 1 place left, end will become 0, the rest will be shifted, so the result will be 170. Next topic is 2's complement. Let's do it here. Previously, binary numbers were only positive. 2's complement is used to represent the number in negative. It uses 8-bit registers. So we will be using 8-bit 2's complement. Leftmost bit represents sign. So the leftmost bit will be 0 for the positive sign, 1 for the negative sign. Range of 8-bit numbers is minus 128 to 127. What it means? It means minus 129 or plus 128 do not fall in this range. Any number lesser than minus 128 or greater than plus 128 can't be represented in 8-bit 2's complement value, as 2's complement is used to present negative numbers. Positive numbers in 2's complement. If we take the 2's complement of any negative number, that becomes our positive number. Same as normal binary, leftmost bit will always be 0 if in 2's complement number. 19 is a positive number, 4 is a positive number. Okay, so convert positive denary to binary. We have another positive denary that is converted into binary. You know how to do that. You have seen it in the first 2 lectures. And convert binary to denary. This is how we convert binary to denary. But let's say now negative 2's numbers in 2's complement. Use minus 128 column. Okay, we use the leftmost column as negative. This is how we use. This is basically the direct method for representing 2's complement in binary numbers. Okay, let's say this is a 2's complement number, means this is a 8-bit negative number. How we add it? uh, if you take this value 1, double it, it becomes 2. 1 plus 2 3, and double the 2, it becomes 4. Double the 4 becomes 8, and then we have 16. 16 plus 3 19, and then plus uh, 32 plus 64. The values above zeros are not added, and this leftmost significant bit, we've used the minus 128 here. Minus 128 plus 16 plus 2 plus 1, that is minus 128 plus 19 gives us answer minus 109. This is how this number's 2's complement is representing that number. What we do now, let's do the standard method. If we want to convert any number, display any number in negative, what we do, convert number to a positive binary, then invert the bits and add 1 to that. The positive binaries, 67, if we convert 67 to binary, that becomes this number. Now if we invert the bits, inversion means we convert 0 to 1, 1 to 0. 0 1 will becomes 1 0, 4 zeros will become 4 ones, and 2 ones will become 2 zeros, because anywhere where there is 1 in the positive number, we invert it to 0. And finally what we'll do, we'll be adding 1 to it. This is how, now we have added 1 to it, and the end it will become 1 1 0 1 1 1 1 0 1. So this is our final 2's complement number. If we consider minus 128 here and add the rest of the ones to that number, so we will get minus 67 as the result. Again, this is minus 79. We convert it, we invert the bits, 0 to 1, 1 to 0, 0 to 1, 1 to 0, 0 to 1, and again 1 to 0, 1 to 0, 1 to 0. Now finally we add a number, so for the final digit will become 1. So 1 0 1 1 0 0 1, and this is how. And most significant bit is representing negative number, so we take that as negative 128. So 2's complement works for any number of bits. For example, even if we have 4 bits, if we take the leftmost bit as the negative, it will work for that as well. Now we have to convert 39 to 8-bit binary. 39 will be converted to 8-bit binary by using the table method. You can study that in the lecture 1 and lecture 2. Convert to denary. Now we have to convert that into 2's complement. Let's take the 2's complement of this number. Now in order to take the 2's complement, what we are doing, we are inverting the bits. 1 0 1 0 0 1 1 0, it will become. So convert normally. So if we, okay, okay, this is the 2's complement value of this number. Okay, okay. So even if we take the leftmost number as minus 128, this will give us the correct result. Okay, let me recorrect it for you. Convert the denary 2's complement. This is the next question. The number 0 1 0 1 1 0 0 1 is given. Now the leftmost is the sign bits. We take it as negative 128, but still as it is 0, so it will not be added, and we add them simply, we get the answer result as 89. So even this 2's complement number is representing a positive 89 number. Convert minus 127 to binary. In order to convert minus 127 to binary, we will first convert 27 into binary. Plus 127 is converted into binary, that becomes this. You can study it in lecture 1 and 2. And now next what you do, you invert the bits. Now when you invert the bits, this will become 1, rest of the bits will become 0, and you add 1 to it. When you add 1 to it, it will become 1 0 0 0 1. This way, so this is the most least significant bit, that will be 1, and then double it 2, double it 4 double it 8 16 32 64. Then here will become 1 minus 128. Minus 128 plus only ones are added, plus 1 will give us the result minus 127. So this is the 2's complement, negative 127 value. So this is our right answer. First bit is equal to 1 gives us the negative number. What we do, we put the minus 128 there for 8 bit. Find magnitude. This is how we find the magnitude of a number. Then invert, and then we add 1. The answer becomes 3. So what will be happening? This is another question that this is the another question of representing this number in this 2's complement number in denary. Okay, what we have done here, we have first converted this number, inverted the bits by converting all of them. So when we inverted the bits, this becomes 0000010. And when we in 2's complement, what we do, this is the number that is shown in 2's complement. If we take its 2's complement, then it will represent the positive number, because its most significant bit is all 1, so it will be negative number. But the most significant bit, we if we convert it into a, take its 2's complement again, it will become the positive 3 number. So the result means this value is representing minus 3. Okay, you will have to solve these examples, as they will help you in solving your exams. Thank you.